So what I want to do now is to recap the computation that was done in tutorial for the gradient, namely this computation. Here's how it goes. So what I want to do again is to compute the gradient of the total cost function, so the cost function for all the cases in the training set or in the mini batch with respect to W. So at first to a particular W or J, and then for all the W's. So this is the expression. And what I want to do is I want to recast it as a matrix expression. So here's how I'm going to do it. I'm going to write out the matrix of all of those terms. So this term is xji times the prediction for the ith case minus the actual value for the ith case. So you have, those are indexed by ji, this is indexed by I, so I can write out the matrix. So in this case, the j's will go this way, and the i's will go this way. And what I want to do in order to compute this expression, so the summation, is to say, okay, so in order to do the summation, what I need to do is I need to sum up along the rows, right? So I'll get just one column as my output, and this is the NumPy or the MATLAB as well notation for that kind of thing. So I'm saying sum up along dimension 1, so along the rows in order to get the result. And indeed, if you sum up this thing, what you would get is you would get the cost total by dw1 or 111. So j equals to 1 here. Okay, and here is the general case. So this is what I want to do. I want to elaborate this a little bit more. So again, this is what we're computing. So what I'd like to do is I'd like to say, all right, so this is what I want, and I'll decompose this matrix into a entry-wise multiplication. So this is not going to be matrix multiplication, it's just going to be one matrix times another matrix. And one matrix is going to be just those terms. And those terms, you'll notice, actually, they're the same along columns. So this is the same term for the first column, the same term for the ith column. Why is that? Well, because this term just says the prediction for the first case minus the actual value for the first case, and it doesn't matter what the j is, it's always going to be the same. So this thing is always going to be the same. And I also want a matrix just of the x's, which is just going to be x, right? So it's going to be xji in general, which is how we store our x's. So to remind you, let me run this again. And let me just change my x. The shape of the x is now going to be like this. Okay, so the j's, which is the dimensions of the x for a single training case, go along the columns, and the i's go along the rows. So this guy is going to be just x. So what do I want to do? What I want to say is I want to compute this kind of thing times entry-wise. So this times this, and then this times this, this times this, this times this. Now, this guy, one column is just this column. The x is just the x. Let's look at what those are in Python. So here we have y minus theta.x. So here we have the minus, which is why those are in a different order than what you see in the slide. So if you compute this term, this is the kind of thing that you get. You get 323 values. So for each training case, you get the difference between the y and the prediction using the theta and the x. And what I do now is I just multiply it by x. So the multiplication in Python here just means generally multiply the matrices entry-wise. Now, obviously, the shape of the x is different. The shape of the x is like that, which is why Python just automatically assumes that what you want to do is you want to replicate those columns of the of the wtx minus y in such a way that you could do the entry-wise multiplication. And what we would want to do then, like we discussed before, is to sum up along the rows in such a way that eventually what we'll get is we'll get a single three-dimensional vector of the derivative of the cost with respect to the w.